When we developed our differential equation to model a mass suspended by a spring, one of the assumptions we made was that there was no friction involved, no air resistance, no energy dissipated by the spring moving around, and that's not very realistic. So one thing that we should do to modify our model is incorporate some sort of resistance or friction. There's more than one way to do this, but if you look at the differential equation that we developed, so it was, let's see, mass times second derivative of position plus spring constant times position equals 0. And if you think about what sort of equations we like to solve, that being linear equations, the sort of obvious thing to do is have some sort of term that has y prime in it. And that actually makes sense because a term with y prime in it, if we have some constant here, let's call it beta, if we have some constant beta times y prime, what we're saying is that our resistance term or friction term is proportional to the velocity at which the mass is moving, which kind of makes sense. Air resistance, at least, is proportional to, well, under some models of air resistance is proportional to the velocity at which the object is moving. So this seems like a not totally unreasonable way to get some sort of friction or resistance into the game here. So beta is just some constants that represents the strength of the resistance. And let's see, if we're using newtons, meters, and kilograms, then beta, so y prime is in meters per second. And so beta has to turn meters per second into force units, or newtons. So beta has to be in newtons per meter per second. Or in general, force units over velocity units. So that's how we can get some resistance into this harmonic motion situation. This kind of resistance term, this is called a damping term. And this kind of damping in particular is called inertial damping. Depending on how you model the resistance in your system, you might not end up with a term exactly like this, but certain kinds of resistance are nicely described by just a constant times y prime. So that's for our mass and spring picture. If we want to add some sort of inertial damping, we can just add a term that's proportional to y prime. Okay, but what about our other favorite second order linear type system, and that would be an RCL circuit, a resistor, inductor, capacitor circuit. So still we're going to stick with our voltage source being 0 just for the time being. Remember that current is the time derivative of charge on the capacitor, right? Q is charge on the capacitor in this situation. So when we wrote down Kirchhoff's law without the resistor, we got, so the impressed voltage, which is 0, has to be equal to the voltage drop across the inductor, which physicists tell us is inductance times second derivative of Q. Okay, and then plus the voltage drop across the capacitor, which is 1 over capacitance times charge on the capacitor. So the only thing that changes when we add a resistor to this situation is we need to add the voltage drop across the resistor. And if you happen to know Ohm's law says the voltage drop across a resistor is the resistance times the current through the resistor. So resistance times, but remember the current is dq dt. So you can see in this RCL circuit, adding a resistor also just adds a Q prime terms. So just like in the mass spring situation, resistance gave us a Y prime term. In the circuit situation, a resistor gives us a Q prime term. So when we go to analyze the behavior of these sorts of situations, when we account for some sort of resistance, we will have the tools to do it because this is still a second order constant coefficient linear equation.